Welcome back, Gangies. This is how we're moving. We're posted up in 2023. Uh, we're in bed, and this is just how we're gonna be moving forward. So, yeah, we're in full viewer hostility mode. Uh, and there's something really funny about that, but you know what? I think that's kind of where we're at. So, we're in bed. We don't have any comments unfortunately, so we won't be able to stall the session. That's okay. I think I'm feeling okay to jump into it. But yeah, this is how we're doing it. We're posted up in bed. So something is really funny about this to me. I'm not exactly certain why, but you know what they say, you got to get it where you can. So this is how we're going to be moving. If you find someone doing LeetCode and they're sitting down, like a caveman, you're gonna tap them on the shoulder and say stop it and get some help, because I mean we're doing LeetCode in bed in 2023. So we're gonna start doing some checks in Discord. If you start your LeetCode session, we're gonna ask you to send us a picture, and if you're not laying in bed, you gotta go. So that being the case, we don't want to get kicked out, so that's where we're at. But we're gonna do a standard 30-minute banger here, and nothing crazy. Somehow, I'm relatively certain if we were doing an hour, we would be making so much more progress, because the last few days we've been doing 30 minutes and we've been able to do about 2 to 3 problems. Where we used to be able to do 2 or 3 problems in an hour. Now we're doing 2 or 3 problems in 30 minutes. So you could probably do 6 problems a day times 10, be 60, 10 days, right? 180 problems in a month. In 2 months, we could finish all the easies, which would be pretty epic. But we have other things in the pipeline, and they must all be given a right. So we have robot origin. I think we did this one yesterday. Oh yeah, we're working on determine matrix. Determine where the matrix can be obtained by rotation. So we pretty much have to rotate this matrix, right? We're given a matrix that's going to be n by n, and we're given an output matrix as well. And we pretty much have to see whether or not the input matrix can derive the output matrix with an unknown number of rotations. But we know that we can only rotate something 4 times before we end up, or let me see, 1, 2, I think 4 times before you end up at your original rotation. So we pretty much just have to rotate the matrix 4 times. On each rotation, we'll check if it matches, and once we run out of rotations, if we haven't matched by then, we'll return false. So that's kind of where we're at with that. So to make that make sense, we have a basic scaffolding here. We have find rotation, the number of rotations that we're counting for, and the number of rotations that were allowed, which is going to be 4. Another way we could do this is just, I'm realizing now, this doesn't even make sense for this to be a while loop. You can just say rotation equals 0 and rotations are less than 4, rotations plus plus. I think we had something different in mind when we made a while loop, but fortunately we don't have to worry about that anymore, right? If we make it out of the loop, we have to return false, because it means the matrices were never the same. So we have rotate matrix here, which is what we have to implement. It's going to rotate the matrix in place. And I think that's basically caught up to where we're at. So row becomes column, and I think that's what we were doing. So we know that this, if we know that this row, right, row 0 becomes rotated and it becomes this column. Now the way it becomes the column is by it's n by n, right? If we're in the 0th row, we know that this row is going to become the mat.length minus 1, which is going to be index 1 here, minus the row, which is 0, which is going to give us the last column at this end, right? If it's going to give us the last column, and we actually may need a new matrix to place it in, I'm thinking. So we probably can't do this in place. So we'll create another matrix here. So we'll create an empty array of numbers, right? And then we're going to do r.push. An empty, we're just going to put 0 here, right? And at the end, we'll just do r, and you'll do output.push r. And then on completion, what this allows us to do is return output. Alright, so now that we know the row becomes the column that we should be operating on, this horizontal iteration now needs to become the horizontal iteration, which was first done as part of the columns, right, 0, 1, going from left to right. Now it needs to be translated into a vertical iteration. So we know that the columns that we're working with need to become the row, right? And I think with that being said, we should be able to solve this, right? So we know that we're going to have some initial row and column that's going to be here in the initial matrix that we're going to have to translate into a new row and column for the following output matrix. Now, how do we do that? I think if we write some code, we might be able to figure it out. So we know that the cell value, right, the cell value at mat sub row sub call, which is going to be 0, needs to be moved on to into a new value, right, that's going to go in output. So we know, right, that like we said earlier, the row changes. The original cell's row will become the column that we're working in. It's going to be mat.length -1 minus row. Now the column that we're in I think from there we could still reuse the same columns, right? So we have column 0 here, right? 0, 1, and we're placing it in the output matrix, which is going to be the rotated one. We can also just keep and use that same 0 and no, okay. I think it would actually be like this, because the column is going to be predetermined. It's the row that's going to have to change, and the row should become the column. So here we have 0, 0. Right? 0, 0. So now we're going to say output, we're going to put, it's going to equal cell value, right? So call, output sub call, which is going to be 0, sub mat.length, which is 2, minus 1, which is 1, minus 1, which is 0, is going to place this at row 0, column 1, right? Which is good because it places the 0 here. Now let's look at this 1. This 1 should end up down here, but we're going to have output sub call. The column here is 1, which means that we should be in output sub call, which is 1, which means we're going to be in the second row here in the output matrix, which is good. And then we're going to stay in mat.length minus 1, which is 1, minus row, which is 0, which is 1, which is going to keep us in this row here. Now the final test is if we go to this one here, we're going to be in row 1, column 0. So this one should move up here, which means that output should go to call. The column that we're in is in 0, so we're going to be in output sub 0, this first row, with mat.length minus 1, which is going to be 1 minus 1 is going to be 0. Just going to place it here, and I think we actually have it. Well, let's see. Okay, so we were able to actually make this make sense somehow. Fortunately, this is pretty dope. The problem is, though, if we ever actually have to do a matrix problem, if we ever actually have to do a matrix rotation for real in an interview, this would actually be torturous because there's something very unintuitive about matrix rotation. But now we know it can be done with at least a small amount of code, which isn't too crazy. We're basically just iterating over the matrix and then swapping the column with the row. Which is interesting. Ah, this is beautiful. So this is yeah, I think in the future we're going to keep this one in mind. So when we need to do a matrix rotation, we can simply take the transpose of the matrix and then reverse each row. And that is a much simpler implementation to remember than whatever we just did. But I'm pretty sure the transpose of the matrix is when you swap the rows and the columns. But I think that changes the shape of the matrix. I is less than n, j is equal to I, j is less than n. Swap the rows and the columns. I equals 0. If we have the same matrix from the original, I equals 0. I is less than n, I plus plus. J is equal to I. J is less than n. J is equal to I. There's no way. This transposition operation is crazy. How does this make sense? Transpose of matrix, reverse each row. I think we've done the transpose operation before in another problem. I think it's literally called transpose matrix. In transpose, the rows become the columns. And the columns become the rows. So if we have 0, 1, we want to swap 0, 1 with 1, 0. If you have 0, 0, the diagonals don't get swapped at all because they're the same. If we have 0, 1, we swap with 1, 0. If we have a slightly larger matrix, if we have sample 2, 0 here, we swap this with 2, 0, we swap this with 0, 2. What about 2, 1? 0, 1, 2, 2, 1, we swap with 1, 2. So this 0, we start with 1. You know what? Or maybe our version is fine. We'll take this. So we're given an array of coordinates. Coordinates sub I is equal to x, comma y. Given an array of coordinates. Coordinates of I is equal to a tuple of x, comma y, where xy represents the coordinate of a point. Check if these points make a straight line in the xy plane. They would make a straight plane. They would make a straight line, right? If the x and y difference was uniform, right? Maybe not. You could have a point over right after 1.1 comma 2. That would be like 1.5, 2. 1.5, 2.5. Which would also still be on the dot. I think we could check if it's a straight line if we calculate the slope of the line and then determine if the point lies on the line. Calculate slope of line, then iterate through coordinates and check if point lies on line. How do you calculate the slope of a line? I think it was y equals mx plus b. I don't remember what b is. B is the starting point. One comma two, 2,3, 3,4, 4,5, 5,6, 6,7. Check the point lies on line. Y is equal to mx plus b. Not certain what. A couple of these math ones are giving us some trouble. We're not guaranteeing a uniformity of distance between the points, so it doesn't make sense to check something like that. Y equals mx plus b. Y equals mx plus b. Y equals mix plus b. We have an x value, and we just need to take this x value and get it to y. Let me check if we can find the formula for the slope of a line. Okay. It looks like the equation to find the slope of a line has nothing to do with y equals mx plus b, but we're in the right section of math. It looks like the equation is m is equal to y sub y2 minus y1 over x2 minus x1. And then I think from there we can also use this value. Once we have m, we'll have m, x, and y, and then we can use it to calculate b. So it's looking like the formula is m is equal to y2 minus y1 over x2 minus x1. Let me just double check real quick. Right, so we'll try that. So we'll just say that x1 and y1 is equal to coordinates of 0, and then let's check if we even get at least minimum 2. Given that minimum 2, so we're probably telling us that we can calculate the slope. We'll say m is equal to y2 minus y1 divided by x2 minus x1. And then we can use to plug it back into the formula. Right? We can say that we want to get mx over to the y side. So I think we can say y minus mx equals b. Say b is equal to y1 minus m times x1 equals b. And now to check that these points lie on the line, I think all we'd have to do is pump all the x values, right, capped on the largest x value, and the y values. So I'm thinking we could also load the coordinates into the set. That way, if we calculate its coordinate, then we'll know that we can exclude it. Hopefully, the coordinates are only integers. And I think they are. Wait a second. This would take a very long time to check every single point. You know what? Something else we could do, take less time. We could sort the coordinates. If we sort the coordinates, just based off x, maybe we want a better. We'll sort it based on x just for now, which should relatively sort this for us. And then we can just check this. We can just check this, calculate the slope for every pair of points. So we'll say let I equals 1. I is less than coordinates dot length I plus plus, right? And we can pretty much copy everything in here. Then we can say temp y2 minus temp y1 divided by temp x2 minus temp x1. Temp x1, and then here we can just make sure that they all match the original slope, and if they don't, and we're going to change coordinates, right, to be I minus 1, if temp b does not equal b, or temp m does not equal m, we'll return false. And then down here we can return true. Aw, man, we were so close. Zero, zero, 0, 1, and then 0. Output here should be false. The expected is true. That doesn't make much sense. The point at 0, 0, a point at 0, 1, and a point at 0, negative 1. Unless we're supposed to ignore zeros. Oh no, it's going straight up. It's 0, 0, 0, 1, and 0, negative 1. It's a line that goes straight up. I wonder why this doesn't work. Oh, so you have infinity and non. Hmm. Oh, I'm thinking. I'm thinking we'll stop there for today.